actually find myself in a slightly strange position giving this talk because, like a lot of physicists, I'm actually a failed astronomer. What I really wanted to be when I was in high school was an astronomer, but it never actually occurred to me that you could actually earn money by being an astronomer, so I decided to do something safe. And I guess over the years I've sort of drifted back towards astronomy, and particularly over about the last 10 years. And the reason for this is that I'm a particle physicist by training, and something rather peculiar has happened over the last 10 years. Basically, we understand everything. This is an extremely embarrassing position for a scientist to be in. It means you don't have any employment. The situation's worse than that. In particle physics, subatomic physics, we have a theory which we know must be wrong. It's wrong on various, actually quite profound reasons, but it always works. And it's got to the stage now where people are simply running out of ideas as to how to test it. But then you look over at astrophysics, and there are these horrendous problems there that no one has the slightest idea how to solve. And quite likely, the solution of the astrophysics problems is going to lie in particle physics ultimately. So that was what got me back into the game. Now, I've been intrigued by this dark matter problem, I guess, ever since I first heard a talk, in fact, by Salpeter at Cornell, I guess about 15 years ago, and that was probably about when the sort of general idea of dark matter hit the scientific consciousness. It had actually been around for quite a lot longer than that. But when it actually started being a problem, people started worrying about it. So, what I'm going to do tonight, then, I had another problem tonight, actually. I've given talks on this a number of times, but invariably to physicists. So what I start off by doing is I start off by showing 10 or 15 or 20 pictures of galaxies, clusters of galaxies, and so on and so forth. You ain't going to get that tonight. You would actually know if I show M31 backwards. Most physicists have never seen M31. So I can get away with a lot there that I can't tonight, so no pictures. What I'm going to do is cover a lot of material very superficially. About the first 20 minutes, I suspect, is going to be well known to every single person in this room. But on the other hand, I've discovered in giving lectures that no one is actually insulted by being told things they already know. They just feel slightly superior to the lecturer, so you're entitled to feel that for the next 20 minutes. The meat of the lecture, I guess, will come in the second half hour when I come and go through the various ideas and tests of dark matter theories. So, lecturing in this room in the past, I know that what you have to do is to turn just about everything off. So I hope this is going to work. So let's start right back at the beginning with Hubble. And what we know is the universe is expanding. The number, and this is going to bedevil the whole of this talk, the number that describes this expansion, this one number, is one of the least well-known numbers in astronomy or in physics. It's not that there are actually now essentially two independent measurements of the rate of expansion of the universe. One gives about 80, one gives about 55. I'm not even going to get into the business of explaining what this argument is or how these numbers come about. But what's traditional in this discussion of the expansion of the universe is, of course, to show these series of diagrams, which I guess date back to Hubble and Humason, mid-1920s, where they looked at 5 well-known galaxies in well-known clusters of galaxies, which everyone has seen, measured the redshift, and then plotted them on a graph. I actually couldn't find a decent copy of this, so I had to replot it myself. Anyone who's taught any scientific subject at any level would know that if a student comes up to you with a graph like that, they have cheated. Like, no one gets a graph that straight. And, well, And the usual thing to do is, of course, draw the straight line first and then move the points down onto it. I don't actually do that. But what you've got to bear in mind when you look at that graph is actually the position of these points is very well known. The velocity of recession is very well known. There's essentially no error in those. The velocity of recession is known to about 4 significant figures. It's this number across there that's uncertain by about a factor of, well, about 30 to 50%. So there's only one uncertainty, and that's that scale along there. Now, why is this interesting? Well, you look out at the night sky, you find that your galaxies are receding, and the ones that are furthest away are receding fastest. So you do an overlay, you draw a straight line back, and you find that all of the galaxies that you see, to a reasonable approximation, were in the same place. The slope of the Hubble, slope of that recession curve gives you the Hubble constant. If you take 1 over the Hubble constant, you turn it into sensible units, you find that's 18 billion years, and that corresponds to the time at which all of the galaxies were in the same place. In other words, it corresponds to the instant of the Big Bang. Wonderful. I should say a little bit about how distances are determined now. Some of this you probably know, but it's worthwhile because of this overlapping distance scale, which is extremely important. The closest stars to us, you determine by trigonometric parallax. You go a little bit further out and look at clusters, and you get what's called statistical parallax. For example, Hyades and Pleiades, you determine the distance to them very accurately by statistical parallax. Cephids, you'll certainly know very well. Everyone has observed Cephids. And that takes you out to about of the order of 1 million light years, 1 million parsecs, 1 megaparsec. It's beyond that that things get a little bit difficult, and the scale becomes more and more dubious. And it's sort of in about here the problems fit, where you start having to fit light curves, clusters of galaxies, and so on. But nevertheless, certainly the first 4 or 5 stages in this are widely believed to be correct. It's this area out here where the distances become very uncertain. Now, I'd like to go through a calculation. This is the only calculation I'm going to do in the course of the lecture, but I think it's intriguing for a couple of reasons. You can ask the question, what's going to happen to the universe in the end? And the calculation you go through is exactly the same calculation that anyone who's done first year physics goes through. You work out the escape velocity from the Earth. How fast you need to throw something up so it never comes back. And you do it as an energy calculation. You say the kinetic energy plus the potential energy must be equal to 0. In other words, when you throw something infinitely far away, it should be traveling with 0 velocity. The calculation you do is exactly the same, except instead of having a stone, you have a galaxy, and instead of having the Earth, you have the rest of the universe, and then you say, did you throw these galaxies away hard enough that they're never going to fall back down? So, how does the calculation go? You simply say, kinetic energy plus potential energy should be equal to 0. This is the critical universe. This is the one which is going to go out. It's just at escape velocity. You know the velocity with which things are going. The mass doesn't matter, it cancels out. So you put in, for this velocity, you put in the Hubble relationship, V equals HR. You then go through 1 line of manipulation, 2 lines of manipulation. You need to work out the mass of the rest of the universe. The density of the rest of the universe is just the mass over 4/3 pi r cubed, the volume of the rest of the universe, and you end up with the density of the universe is 3 over 8 pi, notice the numbers, h squared, that's Hubble's constant squared over g. I find that absolutely staggering. You do 3 lines of high school algebra, and you can predict the fate of the universe. It really is incredible. But there are a couple more things that are incredible about this. The first is that it goes a long way beyond just doing a neat calculation in physics. You're actually learning something very profound. I mean, it has clearly religious significance. It clearly has philosophical significance. And yet the calculation is so trivial. And the other thing is that this calculation could have been done by Newton, easily. I mean, Newton was a smart cookie, we all know. He could have done this calculation 200 years ago. When was this calculation done? 20 years ago. But it's stupid. And what happened was, Einstein came along at the beginning of the century, so every smart person learned general relativity, went off, went through the calculations, worked out the critical density of the universe, got this number, and it wasn't until about 20 years ago that you found you can actually get it in a three-line argument. You don't actually need to go through a term of tensor calculus first. And finally, and this is very unusual in fact, if you go through an argument where you should be using relativity but you fudge it, you get this sort of order of magnitude right. You get it to a factor of 2 or 4 or something like this. In this case, you get those numbers exactly right. You go through your term of tensor calculus and it's 3/8 pi. Amazing. Okay, so what is that number? Well, you know Hubble's constant, you know G. Hubble's constant you measure on Earth. It's flaky to h squared is flaky to at least 50%. So you plug the numbers in and you come up with a density for the universe of about 1.3 times 10 to the minus 26 kilograms per cubic meter. That's not a number I remember. The number I always remember, because it was one that was right when I first learned this, is 3 atoms of hydrogen per cubic meter. In this room, somewhere around 300 atoms, average over the universe as a whole. And just to remind you of how this is going to work, here are the 3 possible scenarios for the universe as a whole. We have the Big Bang sometime in the past. The simplest universe was the one I just described, which is one that was created 18 billion years ago and has expanded at the same rate ever since and will expand at the same rate forever. And that's the open universe. A closed universe is one where you've got too much density. It starts at some point in the past, much more recent, expands rapidly. At this moment in time, it's expanding at exactly the same rate, but it's going to come to a maximum size and then crunch down. And typical sorts of numbers is the big crunch arrives in about 100 billion years, so it's not among your weak stop 100 worries, but it is significant in a way. And the one that lies in between is the critical universe. And to tell which one we live in, all we need to do is to measure the density of the universe. Density is greater than this critical density. The universe comes to a nasty end. If it's less than that, it expands forever. And it's exactly at that, then it expands and slows down, and expands and slows down, and so on. Okay, so this sort of argument was made about, it was taken seriously, I guess, about 40 years ago, and people started wondering about it. And so what did they do? Well, they did exactly what would occur to everyone to do immediately. You just go out and find the average density of the universe, take a large bit of the universe, preferably larger than this room, which is slightly anomalous in terms of the universe as a whole, measure the amount of matter in it, measure the volume, divide one by the other, and that gives you the density. Well, so the assumption that was made is that you look at the galaxies, and you can't measure the mass directly, of course, or you couldn't in these days, so you assume that the amount of light that you get from a galaxy corresponds to its mass. And the specific assumption, and this is the important one that I'm going to be making later on, or I'm going to be talking about later on, is that the mass to luminosity ratio is the same as the mass to luminosity ratio for the Sun. And the numbers that you first came up with for this were that the density is about 2% of the critical density. In other words, instead of instead of 10 atoms per cubic meter, it's about 2 atoms per 10 cubic meters. And this is where the story should have finished. Except, of course, there's a catch in here. Now, some time ago, I was giving a talk on this to a bunch of people in arts and the like, and so I wrote it as a different talk entitled Physics as a Creation Myth, and so I started looking for lots of creation myths, and this is one that I love, because it seems so appropriate to dark matter. This is a Aztec creation myth. There is only a single god, Mixcoatl, whose image they possess, but they believe in another invisible god, not represented by any image, called Ya'alin Ehecatl. I apologize if the pronunciation's wrong. That is to say, God invisible, impalpable, beneficent, omnipotent, by whose strength alone rules all things. It's such a nice analogy to dark matter. Here's the things we see and we understand, but there's something else that we really don't. So, just to remind you, the number I'm going to be using continuously is comparing it to hydrogen atoms, because everyone can sort of visualize what a hydrogen atom is. And the important parameter is this number, omega, which is what the average density of the universe is to this critical number. That's the one that's going to be coming back time and again to talk about. So let's worry a little bit more about how this goes. The assumption that we first made was that the mass to light ratio, the amount of mass out there, is about the same as it is for the sun, and the modern numbers for that give a density parameter, this omega, of about 10 to the minus 2. That was what was 2% on the last transparency. That sort of ballpark figure. It's dropped a little bit over the years. And so now the question is, what's this number really? In other words, how much mass is there out there for a given amount of luminosity? So the first thing you do is to guess. After all, everyone guesses to start with. And the first guess was, well, you look at any of these galaxies. There are a lot of galaxies out there with a lot of crud around. You look at Orion, you can see there are dark clouds there, and you guess the amount of dark matter is about the same as the amount of stars. Also, the sun is a bit more luminous than the average star, so that tells you probably made about a 50% to a factor of 2 error, somewhere in that ballpark. And then there was another, and this was the first observation, that was actually made about 100 years ago, but at the time no one appreciated its significance. Normally, this is a slice through a galaxy, okay? This is a spiral galaxy, so it's coming out of the board towards you there and going back in there. Now, most of the stars just rotate in the plane of that galaxy like that. But the galaxy is about a kiloparsec thick, and there are some stars that oscillate up and down like that. So they're going around the center of the galaxy, but they're also going up and down above the galaxy like that. So they rise up above the plane, drop down below the plane, and the period of that is a few 100,000 years. You then at this stage start making models. You say, well, there's a certain amount of matter in this plane. If you'd thrown up this star so it was going up like this, it's now going to fall back down towards us, because it's got a certain velocity up like that, you can calculate the amount of matter you must have in the plane of the galaxy. Answer, you get about Instead of 1.5, you get about 3. Great, we understand what's going on. The total density is about twice the luminous density, and this, by the way, is the first direct evidence that there's some dark matter there, but no one got very excited about this because everyone knew the answer before it had been started. By the way, this has just been redone, and people get exactly the same answer. Now, the problems really started when people started looking systematically at spirals in the 70s, and this shows the right way up. M51 would be totally useless because we see it side on, but it's useful for illustrative purposes. If you have, we see it flat on. If it was a little bit more side on, you could measure by a Doppler shift the speed at which, let's say you're sitting over here, you're sitting there, this part of the galaxy is approaching you, this part is receding from you, so you can actually measure the speed of rotation in the galaxy. And this has been done by several different means. The best is probably the just measuring hydrogen lines. This shows the results from one particular galaxy. No, I can't find this galaxy. Anyone know where it is? NGC 3198. There's nothing particularly unique about it. It's typical of all the spirals. This shows how the brightness falls off as you go out from the center. Typical spiral galaxy, use M51 as the illustration. The width of the galaxy from the center to the outermost arms is about 20 kiloparsecs, which means that the brightness has dropped off to somewhere around 0 by that stage. If you measure the velocity by the Doppler shift, then what you see is, and this is by looking at clouds of hydrogen gas typically, you see something like this. At the center it's not moving very fast. As you go out, it does something like that. It goes up to a peak there and stays flat. What you'd expect it to do would be to look something like the solid line there. The solid line would say that almost all the mass is concentrated in the center. Once you get outside the central core of the galaxy to the arms, there's not very much matter there because there's not very much light there. So therefore, the rotational velocity will drop off and it will follow a curve like that. Okay, you now drag out a computer program. I had a fourth year student do this as an honors project once. It's a nice calculation. You can run it in front of your eyes. You can juggle the numbers. And what you find is something like this, that the amount of ordinary matter, the amount of disk matter that you can see, looks something like that. And to explain this rotation curve, you need some halo matter that looks like that. And the halo matter is the dark matter that you don't see. Now, there are two bits of bad news here. The first is that your observations only go that far out. There's just there's nothing you can see out beyond that region. Oops. You're right out here, okay? So there's nothing you can measure. And those dots are measurements. But there appears to be matter out that far, and the amount of matter is in fact increasing. And so if you use this to estimate the amount of matter in a typical spiral galaxy, you find not only is there much more than you expected, but also you can't estimate how much more because it's all out here.
How does it compare to the amount predicted by the Z motion?
You mean by just straightforward rate?
By stars oscillating around the plane.
Oh, this is far greater. Okay, I'll come right here. In fact, that's the next thing.
How is it consistent?
Okay, because the upwards and downwards motion is in this region here, where you've still got the disk dominating. Out here, the halo is not playing very much role. So it's a disk that you're seeing when you measure the up and down motion. There you go. And so this mass to light ratio seems to be about 40, and this seems to be true of just about every spiral that's been observed. That 40 seems to be, it's 40 plus or minus 10. Very peculiar. Now, probably the best piece of evidence comes from looking at clusters of galaxies. And imagine the slide of the Virgo cluster, which you've all seen, or the Hercules cluster. You're looking at about 1,000 clusters of 1,000 galaxies in one of these large clusters, maybe 10,000. You can measure the Doppler shifts of an awful lot of them. The Doppler shifts tell you what the kinetic energy is, and then you can use a fairly simple trick in physics, which is known as the virial theorem, which tells you that the kinetic energy, which is essentially the velocity, is simply related to the potential energy, which measures the mass of all of this. So here you go through, you measure the velocity of all of these, of a lot of these galaxies. From that you get an estimate for the mass, and the number that's measured is around 300. That's on the high side. This shows what's happening in the case of one. This is a cluster, I didn't write the name on there, it's one of the Abel clusters, I think. And so you can obviously spot quite a lot of, there are a couple of giant ellipticals there, and there's a foreground star. There are a lot of other ones there. So these clusters seem to be containing about 300 times as much dark matter as light matter. What's very nice about these clusters of galaxies is there's a check on this. The check on this is that there's a lot of loose gas floating around here. And loose hot gas produces X-rays. You can, superimposed on this, there's a plot of the X-ray emission. Well, obviously you're getting some X-rays from the galaxies. That's not particularly interesting. But if you look at this, you notice you're getting X-rays from where there's nothing. The most intense source of X-rays in this galaxy, in this cluster, is where there's no galaxy. It's there. And there's a roughly even distribution as you go out, a nice contour plot. So this is a strong source of X-rays, and completely independently, you can go through an argument that says this cluster must be in thermal equilibrium, you must have a trade-off between the temperature of the gas and the gravitational energy, and you come up with, surprise, surprise, exactly the same number. This is nice because this is actually an independent check that you know what you're doing. And so now the best estimates are suggesting this mass to luminosity ratio is somewhere around, should be closer to, oh sorry, this is for clusters, can be anything between about 10 to 300. So let's say 50 for the sake of argument. If you put that sort of number in, you come up with a value of omega equals 1. In other words, the universe is exactly at critical density. Now, there's this really irritating cliche that every science reporter uses at some time in his life, which is that every scientific question that's answered immediately produces 2 more. This is the only case where I know this is true. The question we asked is, what is the density of the universe? The answer is 1, and the 2 extra questions we get are, what the hell, and why the hell? And that's what the rest of the talk is. By the way, there's a limit on omega. If omega is larger than 3, in other words, if we're 3 times critical density, the universe is younger than the Earth. And probably most of us would not like that as an option. This is the graph that summarizes all of this, and I think it's quite instructive. This is the first thing I gave you, that the solar neighborhood tells us that you've got a mass to light ratio in the range of about 1 to 10. The rotation curves fit you in somewhere up here. The coma cluster and the other clusters fit you in somewhere up here. IRAS actually is a much more doubtful number than that. That's very distant surveys, and seems to be taking you up to there. And notice what this graph is telling you. It's plotted against the size of the things you're looking at. And so what this seems to be saying is that the larger thing you look at, the more dark matter there is. And in fact, you're getting very close to this number of 1. Okay, so, well, obviously there are simply a lot of stars out there that we don't see, etc., etc., etc. No. Now we're getting to a slightly more flaky argument. The matter out there cannot be all in the form of ordinary matter. I'm sorry, this mass density, this density of matter cannot be all ordinary matter. It seems to have to be something else. And the best argument for this, it's a somewhat technical argument, but if you go through the Big Bang, you come up with predictions for the ratio of elements that you see nowadays in the universe in terms of the density. This is not quite the density, it's the density of protons to the density of photons. And as you know, the universe is mainly hydrogen, and it's about 25% helium, so you're sitting up somewhere in this ballpark. And there seems to be a little bit of deuterium and helium-3 sitting around, and that's at a level about 10 to the minus 4. And then at this level down here of 10 to the minus 10, there's lithium. The reason lithium's significant is because you've got a minimum to this curve. And if you juggle the universe a little bit either way, you get more lithium. So it seems very curious that you're actually sitting at this bottom here. That says you can't change the universe very much without creating too much lithium. You can't change it in either direction. And in fact, I've lost a number for that. Oh yeah, okay. The number is that no more than 1/10 of the universe can be in the form of ordinary matter. Now, that's kind of this number's somewhat more dubious than any of the previous ones. I think we could probably wriggle out of this one, but a lot of people take this very seriously. And certainly it's very difficult to get a universe that looks like it does nowadays if we assume the density is much greater than 0.1. Just one final point before I go on and talk about what this dark matter is. If the omega is exactly equal to 1, then you get this figure since the time since the Big Bang. Instead of being 1 over h, it's 2/3 over, it's 2 over 3h. And that's already also leading you to a certain amount of embarrassment, because people have looked at globulars and have analyzed globular clusters in great detail, and globular clusters seem to want to be about 15 billion years old. This is taken from the latest Scientific American. There are a whole lot of people who have been looking at this very carefully now. If globular clusters are 15 billion years old and the universe is 13 billion years old, and we all agree there's about a 20% swap on these numbers, that's all right. But it's getting nasty. So, let's try and answer the questions. What the hell? Now, this is actually a transparency I originally made out 10 years ago. You're not actually getting anything very fresh tonight. It's just to show that a lot of the ideas haven't changed very much. So the first ideas that came up with were brown dwarfs, lots of little stars, hydrogen gas, lots that we didn't see, Jupiters, things that don't quite make us stars, liquid hydrogen, which also you won't see, low surface brightness galaxies, black holes. Black holes come in two flavors, maxi and mini. And then come the particle physics explanations: neutrinos, axions, WIMPs, magnetic monopoles. And the overlay that goes with this was also made 10 years ago. See no reason to change it. We don't see any brown dwarfs. I'll be much more specific on these in a few minutes, but we don't see any brown dwarfs. Hydrogen gas we can observe like crazy. It will give it 21 centimeter lines. There's just not enough 21 centimeter line out there. Jupiters. If you believe it's Jupiters, you better have a very good explanation as to why you form things at 100th of a solar mass or 1,000th of a solar mass, but you don't make stars at the same time. Hydrogen rain. Well, liquid hydrogen could exist out there in large quantities now, but only because the universe has got a bit colder. It could never have formed originally. Low surface brightness galaxies, just aren't enough of them. Mini black holes, these are things created at the time of the Big Bang, Stephen Hawking predicted. They're not made in large enough numbers. Maxi black holes would do the job, but they only occur in the center of galaxies, and that's precisely where you don't have the problem. You have the problem in the halos. Neutrinos, if I am to put money down, I will still put my money on neutrinos, but there are a lot of problems with having neutrinos. And finally, all of these more exotic things, in a moment of frivolity I wrote down, and there is a tooth fairy. Perhaps that was a little extreme. So let me be a little bit more careful about this. There are three options that remain that are being looked at very seriously. Hot dark matter. There are a variety of exotic particles, very light exotic particles, that float around, and the canonical ones are axions. I won't bother telling you where they come from. This is a game, by the way, that's been played by a lot of people. It's essentially a game the whole family can play. You take a theory of the known standard model for particle physics, you tweak it a little bit, you add on some things, you make it so that it's a sort of superset, and then you find, hey, I got an extra particle. That's called dark matter. So there must be literally 50 candidates for this. I'll give you some sort of generic ones. These are no-name-ons. They come with little yellow labels on from Loblaws. And oh yeah, and of course half the problem with this is thinking of appropriate names. WIMPs are obvious, but once we had WIMPs, clearly we had to have machos. Firstly, why don't I believe in brown dwarfs? This is what you see if you look at the stars in the vicinity of the Sun. This is in terms of solar mass. So this corresponds to, this is numbers per cubic parsec, I think. Probably. Yeah, per cubic parsec. So there are not very many solar mass stars, and here you're moving down into red dwarfs. And yeah, you get more. There are about 10 times more stars with about half the solar mass than there are with the solar mass. But then this curve seems to level off. And I think that looks a little bit phony to me, actually. But anyway, there don't seem to be large numbers of objects down about 1/10 or 100th of a solar mass. Now, supposing your theory says that you want that all of the dark matter is brown dwarfs, then you've suddenly got to have this curve turn up and go up 4 orders of magnitude. So the curve would suddenly jump up to there. It looks kind of implausible, but we'll have a better test in a moment. This is an experiment that's just starting to run very soon. It's an extremely clever idea. So clever that I'm almost certain it won't work. Let's not worry about what the size of these things are. We'll call them, these are the machos, the massive compact halo objects. And if you want to relate them to something more familiar, you can think of them as Jupiters or brown dwarfs, or something around 1,000th of a solar mass. Maybe there are several brown dwarfs. And the idea that's very clever is the following. You look at the Large Magellanic Cloud, where you've got around 1 million stars, and if one of these machos passes across in front, you'll see the star flicker. And it'll flicker because the light will have two gravitational paths it can take. When it's right in front like that, this is general relativity, the light can either go that side or it can go that side, and you'll see that star, you won't see it as two images, which would be too good to be true, but you'll see it suddenly brighten. And in fact, as the star goes a little, as the macho goes a little bit further, it will suddenly darken. Now the one thing we really learn how to do, we haven't got much better at actually observing things. The dimmest objects we can see quicker with CCDs, but we can't see an awful lot dimmer than we used to be able to. But what has made this experiment possible is basically electronics. The proposal is to look at 1 million stars in the LMC continuously. Every night that's observing, you're going to be watching these 1 million stars. The sort of effects you expect to get are something like this. Let's say our machos have a mass of about 1 solar mass, then they'll have a radius of about 10 million, it's crazy, 1 million kilometers. And then this effect of the star getting dim, bright, and dim would last about 3 months, which would be easy to see, and you would expect to see about 3 or 4 of these events per year. This is assuming that all of the dark matter is in the form of machos. And you see you can get an incredible range here. You can get down to objects which are 10 to the minus 8 solar masses. In other words, just basically asteroids, tiny little things. And you don't get much micro-lensing. This event will only last 12 minutes, but you get 5,000 of them every 4 months. This is an incredible experiment. I really think it's one of the most exciting experiments ever done, because it may well give you the answer. It's almost an amateur astronomer's experiment, in fact. It's like observing a variable star. It's just you've got to observe a lot more for a lot longer. Watch this space. I don't know any answers to that one. WIMPs. The idea of a WIMP is that you have, it's a weakly interacting massive particle. Again, there are models for this, but you can imagine these things as sort of large in a microscopic sense. They blunder along, they basically don't interact with anything. So they'll go through matter and essentially ignore it. They'll behave, in fact, rather like very heavy neutrinos. Now again, there's a very clever experiment that's just coming on to look for these at Berkeley. I know of one, there are about 3 or 4 others across the world. And they work something like this, that you have silicon, and the silicon is cooled to about 3 degrees above absolute zero. So it's a perfect crystal, and the point of using silicon at that temperature is that if you bang one of the atoms, that vibration will travel through the crystal perfectly elastically. It's what's called a ballistic phonon. So the idea is you have your slab of silicon there, you get the biggest one you can possibly buy, you put it in the dark and you wait for something to hit it. And the signal of these WIMPs, you won't see the WIMP itself, but what you will see is starting from nowhere, this phonon traveling through the crystal, and there are ways of picking that up. I'll give you one more example of another possibility. It's pointed out that you don't actually need to have neutral particles, you could actually have charged heavy particles. And these would be things, let's say, again, 100 times heavier than the proton, but which would form atoms with electrons if you had positive ones, or they'd form atoms with protons if you had negative ones. And again, people have looked for this. In fact, the original experiment for this one was done some time ago by Louis Alvarez, who was looking at the time for something completely different. What you'd see, if you were lucky, would be, this would be a single spectral line, let's say the Balmer series, the red line in hydrogen. You'd see that for the ordinary hydrogen, you'd see that for deuterium, and then out here, just slightly shifted, you'd see this tiny bump that corresponds to this very exotic hydrogen with a very heavy nucleus. You don't see it, so you know to a very good approximation there are none of these champs around. all of these arguments have, and there are a lot of models like this, they all have something in common, and that is that you're seeing something new. You're not seeing ordinary matter. I think it's very difficult now to believe in a model. I mean, I think it's very worthwhile searching for machos. I just don't think that's what the solution is. And one of the other, I think, profound philosophical points of this game is this one. This is the third, maybe even the most devastating revolution for human dignity. I've said man's dignity, I should say human dignity. Copernicus was the first one, with, of course, we're not the center of the universe. Darwin was the second one, we're no different from the animals, we're evolved from the animals. And here's the third one, we're not even made of what most of the universe is made of. That's an embarrassing thought. We really are a minority. I'll take another 5 minutes if that's okay. I'll talk about something which apparently superficially has nothing to do with dark matter. The reason I'll mention it is because it's also a puzzle, and I can't help thinking that somewhere along the line maybe it does have something to do with dark matter. And these are the gamma ray bursters. If you haven't heard this story, it's an interesting one. In the late 60s, early 70s, I guess it was, the US launched some satellites which were designed to pick up gamma rays, and they were designed to pick up gamma rays from atmospheric nuclear explosions. And so they sent the first one up, and sure enough it detected gamma rays, and they assumed South Africa was exploding nuclear weapons off the South Atlantic. They then, a number of these were launched, and a number of deep spacecraft were also launched, and they kept on picking up the gamma ray bursts. And there's a very neat trick you can apply. Gamma rays, it's very difficult to decide anything about directionality because you can't make a gamma ray camera very effectively without about 20 tons of lead. But if you have these things a long way apart, then you can use timing. And so if you have a burst of gamma rays that sweeps through like this, it hits that probe, it hits that probe, and then it hits that probe, and providing you can do your timing, and you don't need to do it all that accurately, you can say exactly where that gamma ray burst originated from. Now, these gamma ray bursts look like nothing we have ever seen. And this is what's awkward. They last anything between a millisecond to 100 seconds or so. They have never been identified with a known object. And when you plot them on the celestial sphere, it looks something like this. This is in galactic coordinates, so the galaxy might look something like that. And these things are just peppered all over the place. They're just totally random. So they have absolutely nothing to do with the galaxy, apparently. Now, it's not very easy to make gammas. Gammas come in with energies of about 10 million electron volts. Too short to be X-rays, so there's some sort of nuclear physics or very high energy physics going on there. So there are essentially three explanations, all of which are lousy. Explanation number one, the reason what you're seeing in this picture here is very distant galaxies. And very distant galaxies, you know, are scattered evenly all over the celestial sphere. And so you're seeing some absolutely immense event occurring in them. For example, you have galaxies where two black holes are occurring. Are colliding. So black hole collisions are occurring in distant galaxies. Well, what's wrong with that? The answer is the amount of energy that you have to produce for this to happen. If you're going to make these, say, galaxies at the distance of Virgo or Coma, you have to put out energies of about 10 to the 54 ergs, which is comfortably more than a supernova does. Now, Firstly, no one can think of any way just to produce gamma rays and nothing else. Remember, these have no optical counterparts. You don't get flashes of light, you don't get flashes of X-rays, you apparently only get gamma rays. No one can think of a reason why this should only produce gamma rays, and no one at all can think of a way that will produce 10 to the 54 ergs of gamma rays and nothing else. So, that seems to be a non-starter. The next one is that these things are very local. They're in the solar neighborhood. So, again, when you look back at this picture, what you're seeing is objects that are scattered around the solar system, let's say at 10 to the 5 astronomical units. What you think of there will answer the Oort cloud of comets. Generally believe that comets originated about a tenth of a parsec out from the sun. And as long as they're evenly spread round, you could imagine that you'd get light from them. Okay, now all of a sudden the amount of energy you require drops down. It comes to something quite reasonable, 10 to the 26 ergs. But comets are made of ice. If you bash two pieces of ice together, you don't get gamma rays. So that doesn't seem to work. And so the least bad explanation, which I still don't like, is that what you're seeing is something from the halo. So the something from the halo might be a cloud of neutron stars. And if you drop crud onto a neutron star, then the calculation suggests you do get flashes of gammas. The numbers become much more reasonable. It's about 10 to the 40 ergs. If you drop a kilogram onto a neutron star, then you get that sort of order of magnitude of energy. You'd get a sudden flash, it would be mainly gammas, and it would be correlated with no known object. So now you've got an entirely different explanation, and this is why it seems possibly significant to me, that here's your galaxy, surrounding this, you have this huge cloud of neutron stars. And it's the gamma rays that you're seeing from these neutron stars. Now, this is not an original explanation, but it's not a stupid one. It's very hard, however, to understand why neutron stars should form a nice spherical halo like that, whereas everything else in the galaxy is concentrated in a nice flat disk like that. That's the difficult bit there. So, just to summarize what I've said, we have some real problems, and here are the three most serious problems as far as I'm concerned. The density one that I've talked about, there's far too little luminous matter to explain the total density, and also we seem to have this other constraint that even if you say there is a lot of dark matter, that dark matter can't be ordinary matter, it must be something much more exotic. 90% of the universe must be in the form of something much more exotic. There's this problem which is just at the edge of being nasty, which is all the stars are getting on for the age of the universe, and if you follow any sort of galactic evolution, it's very unlikely that you form globular clusters that early after the beginning of the universe. They should form later. I haven't talked about this at all, but the Kobe results, which everyone has seen because they were splashed over every single newspaper. What was not pointed out in these is that these things, the fluctuations you see in the blackbody background, are really embarrassingly small. They're absolutely the limit of what your theory predicts. You would like a number about 10 times larger. Another problem I haven't discussed at all, but may have some relation to all of this, is the flatness problem, namely, why is the problem as to why the universe is all at the same temperature. The black body radiation in that direction and in that direction are exactly the same, to 4 places of decimals, which is very hard to understand. There's another philosophical problem. Oh, I forgot to bring my... which is the following. It's an interesting one. I need a ruler for this. I've got one. You have to imagine I'm balancing a ruler like this. And I can ask you, which way is a ruler going to fall? Well, clearly you can't see which way the ruler is going to fall, but it's going to fall that way. Now, whoops, if I ask you to make an observation from the back of the room as to which way the ruler was going to fall, you couldn't do it. But if I let you wait a tenth of a second, so it toppled over like that, you'd be able to tell me it's going to go on falling that way. Now the strange thing is that the universe seems to be in a position like that. This critical density is unstable. That if the universe is a little bit denser than critical density, as the universe evolves, it will get denser. Or it will get further away from the critical density above. If it's less than the critical density, it will go on decreasing. And this makes it very weird that we're sitting right at the critical density. Because if you perturb it a little bit in either direction, it's going to fall away that way or it's going to fall away that way. For some reason, the universe has decided just to stick in the middle. That's why the inflationary universe is a fashionable idea. It predicts this number, omega equals 1. But let me finally finish up with a nightmare. And the nightmare is shown in this graph, which is a real graph. I didn't fudge this. Do we have the slightest idea what we're talking about? This is a result of a survey that came out about 2 years ago now. There are now about 3 similar ones. These are the so-called pencil beam surveys. You look at a very small area of sky, about ½ degree by ½ degree, and you measure the redshift of every single thing in that tiny area of sky. So you're looking at a very small region, but you're looking at everything in it. And what was found when this experiment was done was that you get regions where you seem to have no galaxies. This is in units of redshift, by the way, across here. So you get regions where you have no galaxies. Well, that was no surprise. Everyone knew that already. And you get regions where you get lots of galaxies. Again, no surprise. Those are clusters. But then it's so periodic. These dots drawn along here are drawn essentially every, well, in the units, in inverse Hubble units. So there's a peak there, 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 there's a peak there. Now, if you want to visualize what's going on here, it says the universe is like lasagna. You peer out into the universe, and every time you cut through a slice of lasagna, there's a whole lot of galaxies, and then there's nothing, and then there's another slice of lasagna. No one needs this result. There is no theory that even makes the slightest sense that can understand that. So that really is the nightmare. Thank you.
I guess, Professor Watson, you'll field some questions now. Yes, Fred?
I have a question I'd like to ask you anonymously.
I'll hide behind here so I don't know.
I don't mean the answer, I mean the question. I don't want my friends to think I'm crazy, but see, as I see this, there's a, first of all, may I say I'm glad I'm a chemist. Second, there seems to be a dilemma, but one horn of the dilemma is missing. Every time you look at these radial velocity distributions, you find an anomaly, and it's always assumed that it's due to the presence of some unusual object or mass. And there have been a million crazy ideas, all of which sound totally unreasonable. But no one has ever really, as far as I know, questioned whether Newton's law of attraction is really always true under all circumstances. We know it doesn't work for certain cases of motion, but do we know that there are zones in and around a galaxy in which Newton's law needs another term?
Yeah, there's a guy...
Why does no one ever talk about that?
It's extremely inconvenient, essentially.
That's why I want the answer.
There's a guy whose name I've now forgotten who looked very seriously at this. He was actually in short river for a while. He's permanent at Tel Aviv. I talked to him about
He's
this.
been locked up since.
It's lack of sufficient reason that there's a very simple explanation of why gravitational force is 1 over r squared. It's one graviton exchange. and so you can understand this. But then, if you're going to add something else, you have to add a small repulsive term which increases with distance. You can't get it from anywhere.
Well, you know, we had units of heat, didn't we, back in the last century? The graviton may not be totally pure. Right?
Yeah. I mean, this is certainly true. But you then have to explain why it works so well everywhere else. I mean, for example, Big Bang...
Well, everywhere else, it only works in the solar system. It doesn't work anywhere.
No, there's so much else that's... No, it certainly works for binary stars, for example. It appears to work. I mean, for example, all the cosmological models depend on this.
With a few particles, it works, like the solar system or binary stars.
Oh no, it works with 10,000 particles. For example, you can understand, you get roughly the right proportion of voids to galaxies if you run through cold dark matter simulations. And those are running with 10,000 particles spread over megaparsecs.
I'm not suggesting this is any kind of an answer, but I'm just puzzled why all the emphasis has been on one arm of the dilemma, never on the other.
Because no one knows how to modify it. It's very hard to modify a theory. No, it's very hard to modify a theory that's as good as gravity. Keep the good bits and explain one thing.
Yeah, but then you have all these incredibly artistic particles that are created, which also are just equally strange and unpolite.
It's a very valid point. I mean, I think it's... the only reason for the particles is because you have other theories, let's say, that give you those particles.
Yeah,
those are not created out of the hat. The problem with... I mean, the reason why people don't take modification of gravity seriously is there's no need to. There's no need anywhere else to do it. There's no requirement for your gravity to start behaving.
As long as you're willing to put up with this miracle particles, it's true. But I mean, we've had cases like this in science before.
But even if you modify gravity, you see, you're not getting rid of all of these problems. You're certainly not getting rid of this problem of why the density is so close to critical.
Well, isn't that...
You're also not getting rid of this problem as to why the density is... you're not getting rid of... the density... All right. You're also not getting rid of the problem of why most of the matter is not in the form of ordinary matter.
Well, as for the critical density, that depends on Newton's law, doesn't it?
Not locally.
But generally.
For the large clusters of galaxies, yes. And what you've got to do is to find something or modify Newton's laws over a distance of 10 megaparsecs and will have no effect over shorter distances. That's what the problem is.
Well, I mean, you only have to...
Yes, it can be done.
You only have to fiddle with one law instead of 500 different kinds of imaginary particles. This to me seems to be simple.
But the problem is you're going to run into other problems as well. For example, this hot gas at the center of the clusters. You have to explain why that gas is kept so hot. That gas seems to be kept hot by a very large amount of invisible matter. You're not going to get out of that in terms of fiddling Newton's laws.
Give me time.
Your neutron star explanation doesn't escape the baryonic constraint?
It certainly does not escape that. But that, as far as I'm concerned, is one of the weakest parts of the argument. I think it's... I mean, I'm presenting that as a possible way out, but it certainly does not satisfy all the constraints I laid out at the beginning. It says this basic argument that baryons are only 10% of the universe at most, which means, in this case, it'd have to be 100%. But I think it's a flaky argument.
What do you make of Halt and Arp and his anti-Big Bangers and those types?
Well, that's... Holton-Arp doesn't even have a theory to go with his observations. Holton-Arp's a brilliant observer, I don't think there's any doubt about that. And he's certainly come up with some, well, if you're malicious, you say extraordinary coincidences. If you're a believer, you say extraordinary observations. I tend to think that he's such a good observer that his statistics aren't very good. So he's come up with these extraordinary coincidences, but he's not done systematic surveys. For example, the kind of thing that springs to mind is he's looked at these galaxies which seem to have quasars buried in them. Now, he's not done the same search, such a detailed search, on bits of sky away from the galaxies. So there's no statistical number that tells you the number of quasars you expect to find behind galaxies if you really look hard.
The interesting thing about what you say there is that, if I understand correctly, is that he wanted to do such research, but he got booted off the mountain. You know, he was denied telescope time at Palomar, which for an observational astronomer is like being unemployed, essentially.
Yeah.
So, how do you feel of the treatment he's got from his peers?
Oh, he's treated lousily. That's what happens to every revolutionary. At least they don't burn him. So I think that you need gadflies like that around. But he's also made himself extremely unpopular by pointing out how stupid other people are. And when the person you point out is stupid happens to be on the committee that's giving you observing time, you're probably asking for trouble.
On one of the graphs you showed, it seemed that the distribution of dark matter was almost inversely proportional to the distribution of white matter.
Yeah.
Depth of the galaxy. And is there any particular understanding as to why?
Absolutely none. That's that one where the halo density increases disproportionately with this. Okay, I'll give you one, but if you believe that dark matter is in the form of heavy particles annihilate, which is a not crazy possibility, WIMPs are expected to annihilate, then at the center of the galaxy where they're to be making frequent collisions, you'd expect them to get removed, whereas out here, the density is still comparatively low, even though there are a lot of them, so they don't collide very often. So you can think of mechanisms that will remove them preferentially from the center. This is a sort of second order effect.
Yeah, the annihilation is not detectable.
Yeah, and in fact, annihilation will typically give you high energy gammas. And sure enough, if you look at the centers of galaxies, you see high energy gammas. But there are other explanations. For example, it's easier to assume there are massive black holes there. What you'd like to be able to see would be these things annihilating close by, so they wouldn't be Doppler shifted. And if you then saw a gamma ray with one particular line, let's say 200 GeV, you saw this gamma ray time and time again, you'd be absolutely certain it was an annihilation process which is going on. You know what dark matter was. But there's just not, there's no such thing. You work out the numbers actually, and you're not likely to see all that many. Yeah, sorry.
Another Earth question. I believe another one of his pet lines was quantized redshifts. Seems to me you've just shown some experimental evidence for it.
Yes.
Any comment?
Yeah. This one, actually, the number that he has for this interval is quite different. His, I think, was 35. Actually, I should say that there's the second pencil beam survey finds a periodicity as well, also, but with a different period. It's around 100, h to the minus 1. So that's a different angle to the lasagna.
How do you explain that since the classic background is so uniform?
I don't try to explain it. I certainly wasn't going to explain that. I was just saying.
You know, about those COVID results, I mean, as a layperson looking at those results, there's so much garbage from the instrument itself, and that when you have to resort to these crazy mathematics to see your fluctuations, how seriously can you take those results?
Oh, absolutely. Let me show you why. This is black body radiation world summary of data 10 years ago. Penzias and Wilson are down there. These are other radio ones. These are the first microwave ones flown from satellites. And there was all sorts of stuff about distortions of a black body background and so on and so forth, and how much could you juggle things, and there was photino annihilation in the early universe caused distortion at the high energy end. That's Kobe. That is not an experimental fit. That is a theoretical curve. That is data on a theoretical curve. That is good data. You believe it. There ain't no way out. Probably can't see that. Let me. This shows the stages you go through with Kobe. This was on Physics Today, the original was in color. That's the original one, and that shows temperature differences of, I guess, tenths of a degree. And that's because we're falling through the black body radiation at a constant velocity. It's hot in front of us and cold behind us. We're falling through the circulates. You do the first bit of data analysis. You remove this effect. You drop down to about 100th of a degree, sorry, 1,000th of a degree, and you see this. And what's that? Well, that's the galaxy. And then you drop down, you remove the galaxy, and you drop down, and you see that. Now, and that's the picture that everyone saw. The interesting thing is that if you read this week's New Scientist, someone has done a balloon experiment that ran over the last 5 years. Balloon experiments run much faster because you can put a whole lot more stuff up there, and they have found exactly the same map. Totally different experimental technique, totally different backgrounds, and the map looks identical. It's for real.
How identical is it?
I was under the impression that that was mostly instrumental noise. It was only statistically that they were able to find variations in the actual background level.
Sorry, how do you mean?
The image that you usually see that they say it's a cause of background radiation, the explanation I heard was that the map is actually mostly instrument noise, and that the actual variations that they are talking about are really statistical variations overall. Okay,
I'm told that the balloon flight one doesn't suffer from that because you get, because it's cooled, your thermal errors are much smaller.
So you're saying the balloon flight one was much better than Kobe?
That's in fact what the claim is. Even though the balloon flight was only 6 hours long, instead of being 8 months long, the data taken was of much higher quality during that time. I haven't seen the two pictures superimposed, I have to admit, but the one that I did see looked remarkably similar to this. You've got a big blob in the center.
You're saying they spent a good fraction of $1 billion to do something that they could have done on a balloon?
Yeah. Balloons don't come free, that was...
No, but still.
Besides, balloons aren't as sexy.
That sounded like created a lot of employment.
Can I ask a question? Would this, in the long run, have to modify the Big Bang? You know, they've spent years and years trying to see how the normal baryonic matter was formed, the first 3 minutes and the soup and all this kind of stuff and all this. Well, now with all these exotic particles, they're going to have a different recipe, aren't they?
That's easy enough to run, actually. All you need to do is to take the standard Big Bang equations and you just chuck in some extra mass. And that's already been done. And actually, the concentrations of the ratio of the different nuclei that you come up with is just about what you observe. What goes wrong is if you try and juggle the amount of baryons. If you shove in so that 100% of the matter in the universe is in the form of baryons, then you get the ratios wrong. You have to have a lot of non-baryonic matter, which could be neutrinos. I mean, neutrinos are still my best bet, but they're difficult to see.
Actually, secondarily to the comment about neutrinos, I'm not totally up on this, but there was something about neutrinos. Someone was now theorizing that neutrinos had mass that they had not expected. Would this account for sufficient amount to solve the problem?
In fact, looking for the transparency on the reason I think neutrinos are far and away the best bet is because firstly you know they must be there. You calculate the number that were created in the Big Bang, and it's about the same as the number of photons. In every cubic meter there are about 10 to the 8 neutrinos just floating around. And you can also get if you insist that the whole of the mass of the universe is in the form of neutrinos, then you can say that the sum of all of the masses of the neutrinos is somewhere around 100 electron volts. So that in fact it's quite an economical assumption to say that all of the missing mass, all of the dark matter is neutrinos. And in a lot of ways it's the most attractive one. The only place that runs into trouble actually is in the formation of galaxies. Where if you have a universe that consists of just inert neutrinos, no one knows how to make spiral galaxies. The second, two other comments on that. The first is there's no reason for the neutrino to be massless. There's a very good reason the photon has to be massless. There's no fundamental reason we know of that the neutrino has to be massless. Therefore, it may as well have some mass. So in that sense, it's also economical. But why it should be exactly what you want to do this? Secondly, there have been a number of experiments that have been done over the last 40 years, I guess, looking at the neutrino mass. And about once every 5 years, someone finds a neutrino mass, and then everyone rushes over and redoes the experiment and it vanishes. And in fact, now the best limit on the neutrino mass, well, there are two. One comes from a supernova, because of the neutrinos that came from that. The other one comes from a Los Alamos experiment, and they are actually below that for the electron neutrino. Yeah, I would still bet on neutrinos.
Is any, possible near-term astronomical observation going to provide constraint that's going to shed some light on this problem?
Astronomical, I'm not sure. All of these measurements are going to get better. There are a lot of people now spending a lot of money on doing terrestrial experiments. There are WIMP searches, there are the Macho search, for example, is definitely an astronomical one. So people now have sort of zoomed in on particular explanations of dark matter, and there are now tests that can run on Earth and are running on Earth that will test these, and we'll be able to say, I would guess, and the time scale for these is typically 5 years. In 5 years' time, we'll be able to say there are no WIMPs. WIMPs are in trouble for other reasons. There'll be direct experimental tests that will say there are no.
I once saw in the proceedings of some radio astronomy conference of some description that someone gave a talk on the herd instinct in science. And it had a simulated picture of a buffalo herd. He didn't have a picture of a buffalo herd, but he simulated by putting a whole bunch of pictures of buffaloes and all that. Anyway, he was saying, that brings me to the question of that, since, as you stated in one of your new graphs, that we're not far removed from animals, that was one of the things that really kicked us in the butt. Because of the herd instinct that we naturally succumb to, and I'm sure scientists are no different, everyone seems to be thundering off in one direction. And at one point, you fall off a cliff or something happens, someone takes a different direction, you go thundering off in another direction. What would it take to cause the herd of scientists to go thundering off in a totally different direction to explain? Sorry?
A good idea.
A good idea? I mean, is there something that could happen? What would you see? What would it be? What would it take to happen to give science a boot in the butt and cause it to relook at the way it sees the universe? Is something like an art thing, or something else, or?
Let's take one of our more famous pictures where it seems to show a quasar attached to a galaxy by by luminous matter. If that was for real, then people would be extremely embarrassed. But I think the general feeling is that it's an effect on the photographic plate. Now, there are a number of observations that art was made, and if those claims turn out to be correct, then that's certainly the kick in the butt. But the problem is that other people look at the same stuff and don't see the same things. Other people have looked at that famous bridge of luminous matter and said it's not there. It's just a slightly sloppy technique. That I think it's solarization on the plate, if I remember right. If you're asking what experiment could you go out and do tomorrow, the answer is no one has the slightest idea. And the one I would like to do, if I was given the, and this is one that I've worked on considerably, is I would like an experiment that would observe the neutrino background. Because we know the neutrinos are there. And most of these other things are really far-fetched. They're way out in left field. But the neutrinos are there. We ought to be able to see them. I mean, they're a billion a second going through you. For God's sake, you ought to notice. And so there have been all sorts of ingenious suggestions for how you might see neutrinos. One of the ones that we looked at was that if you look at the polarization of radio waves from very distant radio galaxies, you go out to Cygnus A and beyond, the radio waves are polarized from them. If they are coming through a sea of neutrinos on the way, then that plane of polarization would get twisted. The universe would be left-handed, in fact, like polarized light. There's no such effect, unfortunately. And then you go through the calculations, and this is true for any experiment that's going to look at the neutrinos. Every experiment that's been suggested is about a factor of 10,000 beyond what you can conceive of today. You have to measure forces, for example, that are 10,000 times smaller than the smallest one that's ever been measured. Or you have to see rotation of planar polarizations 10,000 times, etc., etc., etc. That's the answer I think.
Could the dark matter be a combination of the number of these candidates?
I think that's almost certainly true. For example, I think it's quite likely that even if you buy all of this, that 10% of the universe would be ordinary baryonic dark matter. So let's say 1% is luminous, 9% is dark matter, and let's say the other 90% is something more cold. I think that's almost certainly the correct explanation.
You mentioned early on there was the two differing values of the Hubble constant. If you pick one as opposed to the other, how does that affect the dark matter problem, or does it make much difference?
Actually, it tends to scale out. It doesn't really affect things very much because you're calculating the amount you need is scales as Hubble constants, scales as h squared, but also the amount you measure scales as Hubble constant squared. So it tends to scale out the arguments a little bit.
Any further questions? Well, thank you very much, Professor Watson. Certainly we enjoyed this tonight. It's been an outstanding talk. We don't often hear talks that are right on the edge of astronomical interest and research. This is a sort of morals talk today, because I'm sure I may not be around in the next few years. I suppose they'll find the answers to what is today a mystery. Someday it'll be a well-known thing, perhaps written on page 10 of the textbook. So we're looking into the future here. It was very illustrated, very well, and I really enjoyed it. I think everybody else did. So thank you again.